Hey class, so you have your second exam tomorrow, and we won't have a formal lecture. There's not going to be a homework for tomorrow, and so this week your focus will be on the exam. But I did want to take the time to go ahead and discuss progress, just progress in general in the art of science. So I want to lead off with a couple of quotes from Thomas Jefferson. I have them written behind me, but because I haven't mastered the art of writing large enough for you to read what's going on the board, I'll go ahead and read the quotes to you, and then I, I have some thoughts that I'd like to share with you. Okay, so the first one is the the fact is that one idea leads to another, that to a third, and so on through a course of time until someone, with whom no one of these ideas was original, combines all together and produces what is justly called a new invention. And so that was his thoughts on innovation and apparently innovation becoming invention. And in his eyes, no one person is truly responsible for what they create. We are the benefactors the beneficiaries of centuries of work done by other individuals, and it's handed down to us all of this cumulative knowledge. But more than that, the things that are just on the cusp of understanding. So all of our forerunners have done all of this work in math and science and the development of computers and the Industrial Revolution and even our government institutions themselves that support the ability for further understanding. And it's left to us. It's left to the future generations to put those things together. And so we didn't originate many of these ideas, but invention and innovation comes from combining what's already there. So in my eyes, and as I'm quoting Thomas Jefferson to back up my own ideas already, that he agreed as well that the work and the progress comes from understanding and tying together what were formerly disparate concepts and putting them together in a beneficial way. And that's where we get our ideas. That's where we get progress. And I think one of the limiting factors that we'll run into as scientists and students is this idea of an excessive amount of reverence, which leads me to the next quote. Right. So some men ascribe to the men of the preceding age a wisdom more than human, and suppose what they did to be beyond amendment. Right? And so he was discussing the Constitution that was developed. It was written by James Madison, but based on the structure of the Virginia Constitution, of which Thomas Jefferson had a strong hand in developing. And he, the time, I believe, of this quote was around 1816, so it would have been about 8 years after the end of his presidency and about 10 years before he died. And he viewed, or in his opinion, there is, you want your works to be appreciated, but he felt that perhaps there was an overabundance of appreciation for what his generation had done, where in his eyes he felt that it was very much, the Constitution itself was meant to be a living document, and it was all right if people found flaw in it, and that there was this expectation that they would carry on and make modifications. So what does this have to do with really anything, right? With computer science or anything else that we'd like to discuss? So I want to jump into the next subject, and strictly speaking, physics is beyond the domain of this class, which is why it's not really a lecture. It's not even on a lecture day that I'm presenting this thought to you. But let's just for a moment discuss the mysterious concepts of dark matter and dark energy and the Big Bang and all of these ideas that were passed down to us from a previous generation, right? So bear with me. Okay, so there's two equations here. One comes from Planck, I believe, the one on the right, and the one on the left comes from Einstein. So this dealt with the rest energy of mass-carrying particles, and this dealt with the energy inherent in a photon or some unit of light, and that the energy was directly proportional to the frequency, and here the energy is directly proportional to the mass. Right? So, okay, we know that we have some problems. Things happen seemingly in a discrete manner in the quantum world, and Einstein, for all of his brilliance, for coming up with the concept of relativity, and more than that, discovering using Brownian motion as an argument for the existence of atoms, and the photoelectric effect, which is what he won his Nobel Prize in Physics for. And then just as a thinker, the man was absolutely brilliant. He contributed to the progress. But unfortunately, he died before we were given some unified theory, something to tie together quantum mechanics, things that are happening at the nanoscale, and relativity, the things that are happening at the level of star systems and galaxies and stuff like that. And before he died, there was the discovery of a red shift. So the red shift was deemed to be the effect of the Doppler effect. So in sound, and almost everyone is familiar with it, whenever a fire truck drives by, or a police car drives by with the sirens on, or even an ice cream truck, right? You can hear the sound of the sirens approaching, and it sounds different than whenever the car passes you and it's driving away, right? So it's the sound waves are coming together, they're grouping together whenever the vehicle is approaching you, and they're separating whenever the vehicle is moving further apart. And so we applied this logic to light as well. It is our understanding of how a frequency that is constant can be perceived to be changed, right? This idea that, well, if the object is moving, then you'll get a shift, right? And so in terms of light, the equivalent of the siren approaching you would be a blue shift, in that the frequency, the waves, the crests of the waves would be coming together if the object was approaching you, and if it was moving apart, then there would be this red shift. And we analyzed, we looked around, and we looked around everywhere, and we saw that the light waves seemed to be moving further apart. There seemed to be this red shift. But I had a problem with this, just from the idea that, well, okay, if everything is blowing apart, then how is it that galaxies are still crashing into each other? That's something that we observe. Shouldn't they be moving apart too? And if that's so, we see the Andromeda galaxy moving toward us, but we don't necessarily see the same blue shift, at least not to my knowledge. But Andromeda aside, I haven't actually looked at it. I just know the high levels of the problem. But I want to I want to challenge the concepts handed down to us from our forerunners, and propose an alternative, right? So the idea and the mystery behind dark energy and dark matter is that, well, okay, if there is a red shift, then there's some force, there's some driving energy that is spreading everything apart, and that's causing this Doppler effect with light. And mysteriously, the galaxies seem to be more tightly wound than the masses would account for. And so, by our estimate, something like 68% of the energy in the universe is this dark energy that's forcing the galaxies apart, and another 27% is this dark matter that's holding them together. And somehow we found ourselves in this Goldilocks time. And then the remaining 5% is just the energy that we're all very familiar with, right? Okay, so that's out there, right? So we have this dark matter that's holding things together, and we have this dark energy that's spreading apart. We haven't seen any direct observation of it. We just have it inferred from this other concept, and we're using this Doppler logic, which applies to sound and presumably would apply to light as well. And I have no reason to say that it wouldn't. But what I do have a problem with is this invention of energies. So one of the things that we hold fundamental whenever you're going through physics is the laws of thermodynamics, and this concept that energy, it can change its form, but it can't be created. It's the energy that went into it is the energy that came out. Right? And then also at the subatomic level, we have this problem with neutrinos, which seem to really evade detection. But there must be this mass. There's this unaccounted mass that's lost or whatever, and we have this dark energy and dark matter as well. So okay, so what's the problem, right? Okay, so let me propose something else, right? So we have rest mass, right? And mass is the mass carrying particles are what give us the gravitational effect, right? So okay, so then we have some mass, so we have the mass that we know about, right? So we'll call it K because it's known, right? And then the mass that's unknown, right? So this, right? So then our total energy, right? Right, is this, right? So this is what we know about, and then this is really what we're curious about. Where is the rest of that coming from? So instead of calling this mu, out of fear of being accused of an excessive amount of arrogance, right? So the coincidence in the letter coinciding with my last name. Well, okay, we'll change it, right? So let's call this delta m instead. Okay, so we know it's greater than 0 because it has this effect and it's accounting for something like 27% of the mass in the universe, right? Okay, well that's pretty significant, right? So let's call it that, right? And then over here we have something, right? So dark energy is this concept that something is feeding into the system, that we're gaining energy. But if we insist on conservation of energy and the frequency is shifting red, well, then we have this loss of energy, right? So here we have a gain in mass that's greater than 0, right? Which would indicate a gain in mass energy, right? And let me put the subscript here. That's also greater than 0. Right, and here we have a loss in frequency, so we have a delta F, which is negative, right? So something less than 0. Which would imply a net loss of energy. Of light energy, right? So that light energy is going somewhere. Something's happening to it, right? Okay, so here we have something greater than 0. Here we have something less than 0. And if we apply our undergraduate understanding of physics, then we have that the total energy is supposed to be constant, right? So my problem with the Big Bang and with the big rip, or the cold death of the universe or whatever, is that we have to invent this undetectable source of energy But it seems to me, if I was asking an undergrad to solve this problem, I wouldn't invent some new force, and I wouldn't expect them to come up with that either. I would expect them to just equate these two, right? So then, what's the deal here, right? Well, okay, so whenever I was in high school, I was studying, physics with my friends, with my classmates, and we had this discussion, and I think it may have been physics, it may have been chemistry, but we were debating this problem where we were asked to compute like the effective momentum of a photon. We're like, well, momentum is mass times velocity, and if the mass is zero, shouldn't the momentum be zero? But for this process, they're like, well, no, you have to go through and follow these other formula or whatever. But it always stayed with me, right? So, if it has momentum, shouldn't it have mass? But we insist, that that light, it moves at the speed of light. Okay, well, I can't argue with that. But shouldn't it have a mass? If we're giving it momentum. Well, okay. What if we challenge what it is that we've been given? We know that we're missing something, right? So what if this mass, dark matter, is actually, in disguise, this dark energy, right? So what if everything is fixed? What if the position, what if the galaxies, they're moving, right? We see galaxies crash into each other, but what if it's not, this inflationary theory or, this this runaway motion toward a cold death of the universe that, okay, some people ascribe to that, but there's still all these great mysteries, right? We're here to solve these problems. What if they're the same thing, right? So what if this effect is really just, something relating these two? So what would it be? We know for a fact that if we want a unified theory of physics, if we want something that joins together the prospects of relativity with what we've observed at the quantum world, that we'll need to come up with something. If we insist on conservation of energy, then what can we come up with that would actually join these two together, right? And so I've seen, other arguments for the concept of a four-dimensional space-time. And I thought, well, okay, that what is this monstrosity that people speak of, right? Like, what would a four-dimensional space-time look like? Okay, so we'll come back to this. Just keep this in mind, right? So this is kind of our inspiration for developing something new, and we'll see if we can unify the impression of forces in physics into a single theory, into a single concept. Something that explains both electromagnetism and gravity, as well as the mysteries of dark energy and dark matter, and make it all come together under a single umbrella, right? So let's challenge what we've been given, and believe that maybe the generations to come will actually have a better understanding of the universe than we ourselves and those that came before us. But we have to be willing to challenge, right? So okay, so how do we get to a four-dimensional universe, right? How do we get to a four-dimensional sphere? I've really only ever seen it in three dimensions. Convince me that it's possible, right? Okay, I accept your skepticism. Let's jump into it. Right? Okay, so to get to a circle, right? Like in theory, we could do it with just two lines, right? So if you imagine a rubber band, right? So you have something like that. That's a rubber band, but if you pinched it together and you stretched it or whatever, then you can imagine it being two lines that sit on top of each other. And if we use math, well, we'll just make them sit on top of each other with the understanding that there's two lines, right? And so it goes through a transformation where we start to pull the rubber band apart. Or I like to think of it as taking a tennis ball and wrapping it around it, right? So that And it may not look like it, but that last one's actually a circle. It's a perfect circle, right? Okay, so we have the two ends of the rubber band, right? And so we'll label them, right? Right. Okay. So we have Aleph and Bet. This is before the transformation. We have those same 2 points. Okay. So we have west and east, if you want to think about it. But now we have a circle, right? So we have a top and bottom. And we need to represent those as well. Okay, and so we've amended this to include Dalet, which is our north, right? And Gimel, which is our south. But if we insist that this is really the same thing, and we discussed homeomorphisms, right? So we're just it's the same thing. Really, we've just made it look slightly different, but basically it's the same thing that it was before, right? That's what our definition of a homeomorphism is, right? It's a transformation that it doesn't really change anything, right? So here, in our pre-image, we still have those same 2 points, right? And even whenever they're sitting on top of each other, they're there, but it just looks like they're the same, right? So when the rubber band, like before we wrap it around the tennis ball, in order to get to here, from here, right, to get to the North Pole from the South Pole, I have to travel the length of the radius toward Bet, and then I have to travel the length of the radius back toward Dalet, right? So the distance between Dalet and Gimel, the North and South Pole, whenever it's flat, is 2r. But after our homeomorphism, after our transformation, it's going to be a half circle, right? So the circumference of a radius of a circle is 2 pi r, right? So it's half of the circumference. Or if you want to think of it in terms of radians, we're traveling pi radians, right? So from north to south, that's pi, 180 degrees, if you want to think about it that way. And the arc length is the radius times the radians, which is why we in mathematics, we prefer radians over degrees, right? It's because, hey, you can actually compute arc lengths with it, pretty standard. So it's a quarter circumference here, so it'd be pi over 2 length here, and then another pi over 2 makes it pi, right? Or pi times r. Okay, so pi is larger than 2. So I want to emphasize that in making our transformation, everything's still basically the same. The order that you would encounter every point is the same, but we stretched it a little, right? So we went from 2 to 3.14 times our radius. So our distances have gotten a little longer by making this transformation. So, okay, we have a circle. How do we get from a circle to a sphere, right? So now We've gone from two one-dimensional objects to one two-dimensional structure, right? So how do we go from 2 dimensions to 3 dimensions? Well, to get from 1 to 2, we just took 2 of the same thing, and then we found a way to modify it so that it was now something in a higher dimension, right? So is it possible to replicate this and take 2 circles, 2 two-dimensional structures, and wrap it around a tennis ball, so to say, and make it into a 3-dimensional structure? If you're asking Gauss, the answer is no, because you can't make a flat something with flat curvature into something with rounded curvature. But if you're asking a topologist, the answer is yes, because it's just a homeomorphism. It's just a transformation. So we are going to ask the topologist because we're going to need what they know. Okay. Okay, so now we're running into the problem where it's going to be a little bit hard to draw, right? But you can imagine that there's 2 of these sitting right on top of each other, right? And so if you think of it in terms of paper, or you think of it in terms of a balloon or a whoopee cushion, right? So before you inflate the balloon, it's flat. It's just this circular disc, basically. And then you pump in the air, right, and you change it from this flat 2-dimensional object, more or less, into something that's 3 dimensions, right? And so the boundary, where the top and the bottom meet, there's those 2 copies, but those 2 copies share a boundary, right? So the rim of the uninflated balloon is our boundary whenever we discuss this, right? So even though there's 2 copies, these reference points on the boundary of our circle, on the boundary of our disc, they are the same point on both copies. You can think of it as them having been stitched together. So it's 2 copies, but at the boundary, they are the same points on both copies, right? We've stitched them together right there. And now we pump in our air, we inflate it, right? So now okay, so now we've inflated it, and our balloon now, instead of having a top and a bottom, we're standing it on edge, and now we have kind of a back and a front, or a far side and a near side to our sphere, right? And so we call this back point Vev, and we call this front point Hey. Okay, so it looks like pi, but its name is Hey in this context, right? Okay, so now what we've done is on the boundary, the distance between the points, right, from here to here, that's still pi over 2 times r, right? Like, it's still just a circle on the boundary. We haven't done anything to the boundary. We've added stuff to our interior, right? And we pushed those points apart, right? So the distance from here, like on our balloon, before we inflated it, if you drew a circle on the top, in the middle of the top, and you drew a circle in the middle of the bottom, then in order to get from the top to the bottom, you travel from the middle of the top to bet, or any point on the boundary, right? But we'll use this as our reference. So from the middle to the far point on the east, right, to the boundary of our balloon, and then from the boundary of our balloon back to the middle. And so if the balloon, uninflated, was just two circles sitting on top of each other, then you've traveled your radius of those circles from the middle to the edge, and then from the edge back to the middle, but now on the underside. Okay, but now that we've inflated it, okay, so the distance from our middle, right, so this used to be our middle, like if you drew the dots on the balloon and you inflated it, now those points, those dots are still there, but now they're separated, right? So to get from the middle, this is pre-image, this is post-image, or in the image. We travel from Hay to Bet, right, and then from Bet back to Vev. Okay, and so this distance now, it's an arc, and so it's distance pi over 2 times r, and then the distance from Bet to Vev is also distance pi over 2. So now, just like before, right? Now we've stretched our distance, right, by inflating it. We've stretched it from 2r to pi r, but on the boundary everything stayed the same, right? Like if it was on the boundary, then it didn't really change. Okay, so we can understand this. You're with me. You've seen rubber bands and you've seen balloons, right? So that's possible. But now I'm going to ask you to follow the logic and not necessarily what your eyes have taught you to this point, and take a leap with me. Okay, so we did this to get from 2 one-dimensional copies to 1 two-dimensional copy, and then to get from 2 two-dimensional copies to 1 three-dimensional copy. So now if we follow this logic and we carry through, then it should be possible to take 2 three-dimensional copies to create a 4-dimensional structure. So what would that look like? Okay, well, I'm glad you asked. Okay, so now we have 2 of these sitting on top of each other, right? So just as before, you can't really draw it, but you just have to know that they're both sitting on top of it. Okay, and so as before, now we'll take our 2 copies, right, and we'll imagine that there's both this top and bottom, right? And so we'll, in this case, because we already have a top and bottom, right? We have an east and west, and we have a far side and a near side. We're kind of running out of terms, right? But I do like the concept of keeping this top and bottom. So let's dip into our Latin and borrow the terms borealis and australis, right? So we have something that's north and south or whatever, right? So we have our top copy and our bottom copy. And each of them has a center, just as before, right? So the 2 circles had a center, and then whenever we inflated it, they became separated instead of by 2 times the radius, by pi times r, right? And so now we have these 2 copies, and as before, where both boundary and interior, whenever it was inflated, you know, became the surface of our new structure, right? So the outside of the balloon before it was inflated, our 2 circles, remained the outside of the balloon whenever it was done, right? But whenever we went from 1 dimension to 2 dimensions, we had just the circumference, and then in order to go from 2 dimensions to 3 dimensions, we had to include the center as part of our inflation, right? And then it all became the surface. So what used to be the inside became the surface of the higher dimension, right? So that concept is going to stay there as well, right? And so in order to achieve this, I'm going to say, well, okay, we don't actually care what's inside the 4-dimensional bubble that we're about to make. We don't care about the inside of the 4-dimensional sphere. I'm going to suggest that we live on the surface. All we really care about is the surface. So what does the surface of our hypersphere look like? Good. Yeah, let's find out. Okay, so now we have our 2 copies side by side. So yeah, I kind of cheated on this last one. I don't have some way of drawing 4 dimensions on this 2-dimensional surface, but forgive me. But the logic, right? I've asked you to follow the logic all the way along, and so as before, we now know that we have 2 copies, right? And as before, the 2 new reference points, the 2 new poles created by our inflation, have transformed traveling from north to south pole, right, from from the opposite sides of our pre-inflated disk, from a distance of r, to some boundary point, and then r back to the other pole on the other side, right? From our Borealis North Pole to our Australis South Pole, or from Zion to Het over here, right? Our new two poles. So before, our distance was 2r, and now our distance is pi r. So we've again stretched it, right? So the distance from here to here is pi r instead of 2r. And you'll notice that I flipped each of the reference points, right? So when I first, when I first explored this idea, I only flipped one point, and then I realized, well, let me show you, right? So again, the boundary points, just like whenever we were stitching together our balloon, we had a top and a bottom, and the boundary points were the same on the top and on the bottom, right? So the boundary points before we inflated our balloon remained, at a fixed distance. So maybe the balloon's not the greatest analogy, right? Because it kind of inflates in all directions. But if you don't inflate it too much, if you don't stretch it, if all you do is pump in air, then then you can make that claim, right? If you don't blow the balloon up too much. So they remain in the same order or whatever whenever we inflated it, but the distances didn't change between them. What did change was the distance from the interior of our top to the point, like to the interior, the midpoint of our bottom, right? It stretched from 2r to pi r. So again, we have the boundary, right? And in this case, it's the surface of our three-dimensional object, right? So that remains stitched together, right? So those points are actually the same. And so just like in one of those old video games where if you go off the right of the screen, it takes you to the other side, right? So I now have these two copies, but this is what's happening. So if we went from Borealis, right, and we traveled to Bet, then we would actually leave this one on our map, and we would start over here, right, and then we would carry on to Het. And then if we continued in the same direction, right, if we continued moving east, then we would reach a left, and then we would wrap around just over here, right? And so it's a leap of faith, right? But they say that we once thought the world was flat, and maybe for non-mariners, that assumption is true. If you lived, in some landlocked country, maybe you couldn't really see the horizon and imagine that the world could be round. But the idea that you could travel in one direction and then come all the way back where you started, it would probably have seemed completely ridiculous. But there's something going on that we don't understand, right? So let's let the math lead, and then we'll see where it takes us, right? Okay, so the same thing is true, right? Of if we travel from our Borealis point, right, from Zion, and we travel down to Gimel, then this point, right, our reference points are the same, right? Would actually be this point up here. So we'd start up here, and then we would carry on until we reached Het, and then we would carry on until we reached Dalet, which this point is actually the same as this point, right? And so we would continue on over here, right? And the same thing if we went in toward the board, towards Zion, toward Bev, and then this point, again, the boundary, is actually the same as this point over here, right? And so we would carry on, and then we would reach Het, and then we would go from Het to Hay, which is this point, and we would go back to where we are, right? So in any direction, if we went in a straight line, we're now traveling 2 pi r. We're traveling the circumference of the radius, or the circumference of, the great circle with the same radius. So it's just a circle in all directions now. But it's a hypersphere. So we have these 2 copies, and we can kind of imagine, that the world is a little bent now. And we know that our distance has been stretched a little from what was the interior of the pre-image. It's now stretched just a bit. But on the boundary, the distances are the same, right? So the great circles, they still all have circumference 2 pi r. But it's just a little weird because I'm asking you to imagine a 4-dimensional sphere. Okay, so what does that have to do with anything, right? Okay, so now we could kind of discuss, right? So if you have a piece of string, right, you have this 1-dimensional object, and you vibrate it, you have the direction that it moves in. It moves in the 1 dimension that was provided by the string, and now the vibrations are moving up and down. The oscillations are in this new dimension, right? It's up and down, whereas previously we only had sideways. So take a 1-dimensional structure and you vibrate it, and you get a 2-dimensional wave. Okay, so you have a pond, which a pond is flat for its intents. And you drop a pebble in it, and now you have waves, and they go up and down, but they move out along the plane. So you have this 2-dimensional object, and now it's vibrating, it's oscillating, its waves in this new dimension, in this 3rd dimension. Okay, so if you have a 3-dimensional surface, right? A 3-dimensional surface, right? And you vibrate it, you get this up and down wave action going on the surface. Then you have your 3-dimensional surface, and its waves are propagating out in 3 dimensions, right? But the oscillations are again going up and down. Okay, so I said that we would bring this all back to electromagnetism and gravity and dark energy and dark matter, right? Okay, so great. So what are these waves, right? Okay, well, we have this concept of up and down, right? And electromagnetism, it already has these labels of positive and negative. So I am proposing to you that those waves, and we already know that all of these particles behave in this wave manner, are those up and down oscillations, right? So one direction is going to be the positive charge, and the other direction is going to be the negative charge. And so it brings forth all of these other questions. Well, okay, so if the waves, if the crests and the troughs, or as I propose we call it, the aspiration and inspiration of these waves, the up and down motion in this 4th dimension is charged, then what does that necessarily mean that magnetism is, which is intimately related, and we're striving for some unified theory. So then, what is gravity as well, right? Okay, so we have proposed, that there are certain conservation laws that must be observed, and so far the only thing that we've really necessarily claimed is that energy is conserved. But we need something to understand, what are we seeing here, right? And so, in a room, we'll see this kind of diffusion of energy, so that the room, the particles in the room strive toward some sense of homogeneity or uniformness throughout it, right? And so if we were to apply these concepts and we were to use our understanding of how waves move, on the surface of a pond or in the ocean or whatever, we know that the water, or that the thing that's vibrating, it eventually wants to return to some restful state. It wants to be flat, but it's kind of vibrating, and in that sense, despite the vibrations, the surface, it's not actually increasing. We're not getting more water whenever there's a wave in a pond. We're not getting more string whenever there's a wave on a string, and so I'm suggesting that we're not getting more surface of our hyperspace. Whenever we do that, we're getting a fixed amount, right? But it wants to be flat, and so that's kind of what we see whenever the room cools, that it's dispersing the energy in the way that you would expect a wave to disperse if you did it in a cup, right? If you dropped a seltzer tablet into a cup, the wave would it'd do its thing, and then it would come back to settle down. And so that's the cooling effect that we would see. So then, what are photons, and when are you going to get to gravity, right? Okay. So I am suggesting, and at this point, I have no test to say whether or not it is in effect an actual particle, or if it's just a concept. But it's been suggested as well by other individuals, to think of magnetic fields as flow, right? As like a fluid motion, right? So you can think of these field lines and stuff as actually being the current, or the flow diagram of some incompressible fluid moving through that space or whatever, right? And so this has been posited before, right? The Mickelson-Morley experiment famously looked for some luminiferous ether. So something that the waves of light would be vibrating in order to transmit light. Like there's some medium, there's something there that's actually being displaced. Otherwise, you wouldn't be able to have the wave. And so they tested for it, and they didn't find it, and it was this famous negative result in experimentation. And then I saw a diagram of Earth's electromagnetic field as it's moving through space. And so what they were looking for was something that would kind of leave a wake, in the way like if you sent a boat through water, like it has a wake or whatever. And they didn't find it, but the Earth's magnetic field, it kind of looks like water moving around a boat as it's speeding through space, right? So so it seems to me that maybe they weren't so far off. They didn't find what they were looking for, and it got ruled out. And then later on, and before that, there was we were testing for oh no, phlogiston was different. That was for fire or something like that, right? And now we're searching for the Higgs boson. We have this idea that there's something that allows these particles to exist, and something else, right? So what if we disperse with the necessity of coming up with a name, or coming up with a mass or whatever, and we just follow the thought for now, right? So let's assume that there is something infinitesimally small that all of the universe is made up of. And it's the same on the surface as it is on the interior, and because it's it's the universe, it's all of it. It's not necessarily moving. We don't have to worry about bubbles or anything popping up on it or anything, or losing any to the wind, or evaporation, or anything like that, right? It's just a thought. It's a thing that can move around, right? And so as I'm thinking about this, right, and I'm imagining these waves and this displacement, I'm thinking about this putty that I put in my ear whenever I go swimming, and it's this silicone putty, and it you can shape it, and it takes the shape of whatever it is. But as you press on it, as you distort it, as you wedge it into your ear, and it's taking a shape. It's being distorted, but neither the total mass of that thing is increasing, nor is the surface area. So as you push down on it, it does this wave action, right? So down somewhere means up somewhere else, and it doesn't actually create any additional surface area. It just contorts to fit, the displacement. So I'm proposing that whatever it is, whatever this infinitesimally small luminiferous ether is, right, is actually that thing. We can just conceptualize it, right? So in that case, then the charge, the positive and negative charge, is the wave, and the electromagnetic, or the magnetic phenomenon is actually the motion of this it's coming in somewhere and it's leaving somewhere else, right? And so those are the north and the south poles. And while it's being displaced, it follows this path, and it in one end it's going in, and the other end it's coming out. We don't really know which one because it seems to obey certain symmetries, whatever. So there's no real way of telling. But it that would seem to hold, right? So then, how does this tie into gravity? Well, so we have this up and down motion, we have this displacement, and now we're going to add our second proposition, and that is that what Einstein declared, that the speed of light is constant, or would be measured to be constant in all reference frames. But if instead of calling it the speed of light, we said it was the rate of propagation through the medium. So whatever it is, whatever the Higgs boson is, whatever the luminiferous ether is, whatever this thing that is carrying this wave energy is, whatever it is, it's constant through that medium, right? And so Einstein was famously able to declare that time is relative to whatever your reference frame is. So if you're in a reference frame, or in an accelerated reference frame, that time would not necessarily move equitably to the time passing through some other accelerated reference frame. But if we hold constant the wave propagating through a medium, then we would expect it, like if you imagine now like a ripple, through, if you threw a pond into some rogue wave, some wave in the ocean that's like 40 feet tall, you would expect it to have to travel along the surface, and there's a lot of displaced water, and so in order for it to go 20 feet or whatever, for that wave to propagate 20 feet, it's having to travel along this new surface that it's not flat, just as space-time isn't necessarily flat, or I'm encouraging us to call it hyperspace now, but just as hyperspace isn't flat, it's having to travel along this new surface, right? So wherever there's more matter, right, wherever there's this more displaced stuff, this medium, that our constant rate of wave is actually slowed down, not because it's slower, but because it's traveling over a further path, right? So jogging over hills and mountains is not as fast, in addition to the extra energy that you're using or whatever, because the distance is further. Like, you're not traveling on a flat plane, you're now traveling some distance, displaced through a new dimension, right? So those concepts seem to tie together pretty well, but what can I offer in the way of proof for this, right? Okay, so now I say, well, if we know that light is tied to electromagnetism, then and through this new proposition, our electrical charge, and that wave energy that is actually what we're seeing as gravitational effect. It's this distortion, through our new dimension, our fourth dimension, our aspiration and inspiration. So that would cause both the relativistic effects of time that we see and the gravitational effects, because it is accelerating space in that direction, three-dimensional space in that direction. Then we would expect light, which is part of this same phenomenon, to exhibit some behaviors of mass. So where would we see this? Like, there's no evidence. Well, I counter that 27% of the universe is actually serving as evidence for this. So now with these two concepts, a constant rate of propagation through the medium, and a conservation of energy, that the effects that have been perceived as dark matter and the effects that have been perceived as dark energy are actually the same thing. So there isn't inflation, there wasn't a Big Bang, and we're not seeing a Doppler shift. That change that decrease in frequency that we assumed to be the Doppler effect because that was what was familiar to us from chasing after ice cream trucks and stuff like that, is in fact the dark matter. It's this displacement, the light, the mass that light is carrying as it's passing through the galaxies. It has what I'm calling a transient mass. So while it's there, it is displacing space in the same way that the familiar mass carrying particles displace space, but it's waving the whole time that it's going through there, and it displaces space, and it creates that effective mass phenomenon, and because we have to conserve energy, the energy gained by acting as dark matter is observed as a loss as it passes through galaxy after galaxy. It's expressed as this loss in frequency, and so the galaxies, these massive structures of mass-carrying particles, serve as this dampening effect on light as it passes through, and so that's it. That is the challenging of our forerunners that I'm proposing, something that unifies what we have observed in terms of quantum mechanics with what we have observed in terms of relativity. So then, what is this wave that's actually transpiring, right? Like, shouldn't we be able to derive something for that? So we'll end with that. I'll show you what I have in mind, and then that'll be it. You can go back to your exam tomorrow. Okay, so if you want to think about like a drum beat or whatever else, right? So you can imagine this displacement, and then it kind of propagates out and it spreads, and so the vibrations continue at the source wherever that displacement originated, but some of the energy is carried off and some of the energy remains. So we've covered sequences and things like that. So there should be something that conserves energy that represents this, right? So there is a sequence that we've studied that represents an infinite series, and it adds up to 1, right? The geometric series. So each term in the geometric series is of this form. It's 1 over 2 to the n. So if we think of the waves as from flat going to some crest, or you can start with the trough, it doesn't really matter, and then going to the other one. So if you start with the crest, then it dips down, it goes to the trough, and then it terminates, right? So that's one wavelength. In equal amounts, equal height and equal low point, right? Then we can come up with a series of generations of wave propagating out from the middle using the geometric series, so that the total energy of the series is equal to the initial energy that was put into forming the wave or the series of waves, this propagation of waves in the first place, right? So we have a geometric term, right? Okay. So then also, Gauss, as he was studying electromagnetism, he observed that the total flux through a sphere or a three-dimensional enclosure around some source. So if you're considering it, as an electric field or as a magnetic field or whatever the flux is, right? The total energy of whatever passing through that, it's the same, at every point on the surface, right? So we have this Gaussian term that as it increases, then the flux, as it passes through this now larger sphere or whatever, uh, the total amount is the same, but it's diffused over a larger surface area, right? So we have our geometric term, which deals with the generation of wave, and then also we have this diffusion factor from Gaussian surfaces, right? So okay, so whenever we get, so where this is, here, let me change this to lambda, right? So for rho greater than one length away from the source of this energy, we're going to use this. And interior to that, we are going to drop the Gaussian surface, and we'll use just the displacement determined by the geometric series and the sine function, right? So, oh yeah, we're dealing with a wave, so there's going to be sine, right? So then the last part is okay, so then we have a function, g, which depends on both time and distance, or time and radial location from the origin, right? And it's periodic, so at every wavelength interval, it's periodic, so rho over lambda, 2 pi times the percentage of the wavelength that you've traveled from the origin, right? And alternatively, it's periodic with the period, right? So whatever the period is, as determined by the frequency of this wave, it's the percentage of the period completed, right, times 2 pi. So you have this term. So now we have our wave function, this mystical wave function. Okay, so we have our geometric term, our surface area term, and our sine term, right? And then, of course, this is right. So then this is it. Whenever rho is outside of one wavelength, and this is it whenever rho is within one wavelength. And then we actually need these to equate at lambda. They should be interchangeable. So something happens here, right? So we have some value, right? We have something that it is whenever it's equal to lambda. So at one wavelength, it has that generation has some amount of energy. And then as the Gaussian surface increases, it degrades proportional to the surface area of that enclosing sphere. So that's it. Good luck on your exams tomorrow.